Okay, today I'm going to talk about the second part of 8.2 series and convergence. So in the first part we were talking about the definition, and we used the definition to analytically show that series converge. Specifically, we dealt with telescoping series. And then we also used our calculators to numerically approximate series that converge. And then also we were able to determine whether or not they converged or diverged. And you know, you can always sort of test that out using your calculator, running the program, or using the summation feature. And that can tell us sort of, at least numerically, if we enter larger and larger numbers, whether the infinite series converges or diverges. That will not be an analytical proof. Okay, so when we're asked to sort of prove or show that a series converges or diverges, we have to go through specific analytical tests that we're going to start here today. Now, the first is just using the definition, and the only analytical type of situation where we use the definition to prove a series converges or diverges would be with a telescoping series, where we actually find the sum if it converges. Okay. The rest of the time, I will tell you, most of the time we're not even concerned with the sum is analytically. We are going to get to what are called geometric series today, where that is an issue. But a lot of times we're just proving whether series or converge or diverge. And if they did converge, most of the time, if we want a sum, we would have to approximate the sum. We wouldn't know a definite sum. Okay, so let's get into our first test of convergence or divergence. This is what's called the nth term test. So given that you have an infinite series, by the way, you'll notice that I didn't have a starting index. That could start at n equals 0, it could start at n equals 1, it could start at any value. It doesn't matter. If we limit the sequence to infinity and it doesn't equal 0, then it diverges. End of story. So for instance, and if you think about the logic here, let's say I gave you the series infinity n equals 1 of 2n plus 3 over 3n minus 1. Okay, so this particular series, realize that if I look at what this thing goes to for larger and larger and larger numbers, right, if I do the limit as n goes to infinity of this thing, we get 2n plus 3, okay, and 3n minus 1, we get that's equal to 2/3. And, you know, we can use simple AB stuff. We're comparing sort of the strength of the function top and bottom. These are both degree 1, so we get 2/3. Now what that means is, as we get higher and higher numbers, each new term gets closer and closer to 2/3. So if you just think about it as if it actually got to 2/3, if we added up an infinite number of 2/3, we go to infinity. So that is enough to prove. So anytime we limit n to infinity and the sequence, it does not limit to 0, end of story, it diverges by nth term. And that's exactly how we would prove it. So it's the quickest and easiest thing to check, and it's something that as we start getting into all sorts of proving of convergence and divergent series, that's the first thing to check. If you limit the sequence to infinity and get something other than 0, you know it diverges. And that's end of story. Now the one thing we have to be clear, the converse isn't true. Okay, so for instance, if the limit as n goes to infinity of a sub n is equal 0, that doesn't prove convergence. If we limit the sequence to infinity and get 0, it may converge, it may diverge. We just don't know. If you remember, and it's kind of hard to sort of wrap your brain around it, because it's like, oh, if that goes to 0, we're going to eventually be adding zeros, that'll be finite. We investigated, if you remember, 1 over n, okay? And you can try this again, and when we approximated that, plugging in larger and larger and larger numbers, it kept going and going and going. This is actually goes to infinity. So even though this limit goes to 0, it does go to infinity. So don't make the opposite true. So in other words, nth term test only proves divergence. It never can prove convergence, if you want to think about it that way. Okay, so just always keep this in mind. All right. Okay, our next test that we're going to do is called the geometric series test. This is actually a really nice series because it's easy to determine whether it converges or diverges, which we'll talk about in some examples. But more than that, it is the only analytical way outside of using the definition that I have to get a sum. So as I talked about before, most of the time when we're looking at series, we can't analytically find the sum. We have to approximate it. If it converges, that is. But this is the one analytical case where we have this nice, neat little formula that we can actually get the sum. Okay, geometric series, I will tell you that this can be a little confusing for people. It either is typically written in this form or it's written in this form. And geometric series means that we have a ratio, a common ratio raised to larger powers. So I want to point out that these are actually equivalent. What's important is the first exponent. Now, if you think about this, if I plug 0 into this, I get r to the 0 power. That's going to be 1, so that's equal to a plus. Now, if I plug 1 into that, that'll be a to the single r plus, and then I'm going to keep going, r squared plus a to the r to the third, et cetera, onto our general term. This does the exact same thing. So if I plug 1 into this, you'll see my first power is 0, so that gives us 1, leaving us with the a, et cetera, et cetera, et cetera. The reason why that's important, it's actually not important to determine this, to determine whether it converges or diverges. When it matters is, it's very important our first exponent is 0, and if it's not, we're going to have to adjust that to plug it in to get the sum if it is a convergent series. And I'll show you how to, I'll give you an example where we have to do that. So the first thing to check is your first exponent 0? If it's not, we're going to have to do some algebraic manipulation so it is. Okay, so let's do some examples with this. Okay, so for each of these are all going to be the same. These are all geometric series, or can be written in that form. And I want to remind you the form that we look to write these things in, especially if we determine whether it's convergent, or excuse me, to determine the sum if it's convergent, is we either want it in this form, index of 0, okay, or this is equivalent to this. These are exactly the same thing. And this is one of the things you have to get used to with series. We can always adjust the indices where they start by changing our formula here. And there'll be exercises along the way where we're actually going to do that. But they have to be one of these two forms. The big thing to check is your first exponent has to be 0. Okay? And if it's not, then we have to adjust. Okay, so we look at this first one. Okay, so once again, this is our common ratio raised to n. This is ready to go. So this is 0, plug that in. Now, we're missing an a, right? So understand that there's a 1 that we would put there if it doesn't have that a. So 1 times that thing. So what we would say is this series converges. And that is because the absolute value of r, so our common ratio, the thing raised to the power is 3/4, is less than 1. And converges because, and that's by geometric series test. Down the line, this is going to become more important because we're going to get all these different tests, so it's important to say what test. By geometric series test. Right now, it's not so important. And the sum, because it is convergent, we're going to use that formula. So if you remember, the formula is S equals A over 1 minus R, okay? Where this is our A and this is our R. So the sum is going to be 1 over 1 minus 3/4, okay? So this is going to be 1 over 1/4, multiply top and bottom by 4, so this series converges to 4. If you want to do a little experimenting with this and plug that into your calculator and see, you will see that that does converge to 4 actually pretty quickly. Okay, now this one is also geometric, but it doesn't look like it at first. So if I look at that, it's not clear that it is in this form of a to the Rn. So the important thing to do is whatever is raised to the n power, that is our r, and that has to be isolated. So then I'm left with 4 in the denominator. So what that means is that's my a, but it's not 4, it's 1 over 4, right? So I can rewrite this thing hopefully this isn't too busy for you, I can bring this out as 1/4, and then I'm left with 3 to the nth. Okay, so we always want to isolate whatever's to the nth power. And then once again, we check the first exponent to see that it's 0. It doesn't matter here since it diverges. We don't have to worry about finding the sum. That's the only time that really matters. So we would say since the absolute value of r is equal to 3, which is greater than 1, our series diverges by geometric series test. Okay, so that's it. Oh, by the way, if a series diverges by geometric series test, it would also diverge by in term. I want to point out that if I limited just this to infinity, I would get infinity. That's not equal 0, so it would diverge by nth term as well. All right, this last one is going to be a convergent series. Here's the thing, the a is not 1. And as I was talking about, this is the one where this matters. So if I plug 1 in, you'll notice my first exponent is not 0. I need that first exponent to be 0. So what I need to do is I need to rewrite this so the first exponent is 0. So all I'm going to do, all I'm going to do is basically factor out a 1/2. Okay, so that'll give me 1/2. And then if you think about it, this will just be 1/2 to the n minus 1 now, right? So right here I want to point out that if I added these, right, this would be 1/2 to the first. If I multiply them, I'd add the exponents, I would get this. So this is equivalent, but now it's in that form where we see the first exponent is 0. This is our a, this is our r. And I've got to make myself some room here, so I'm going to erase this up here. Okay, so let's do the work for this one up here. So once again, we got to rewrite this thing because the first exponent is 1 instead of 0. That's always something you have to check when you're using the geometric series test, especially the sum formula. So now I would say since the absolute value of r is equal 1/2, that's less than 1, the series converges by geometric series test. And the sum is equal to a, so that's 1/2, over 1 minus 1/2, which is going to give me 1/2 over 1/2, which is equal to 1. If you don't do this, you'll still have the 1/2. If you didn't recognize this, you would still have the 1/2. You would still determine it's convergent. But when you plug this in, you would get 1 over 1 minus 1/2. You would get that this is equal to 2 if you didn't realize we had to bring out a 1/2 to make sure that first exponent is 0. Okay, so that's the geometric series test. Quite easy to use once we write it in the proper form. So once again, really just quite easy. If the absolute value of r is less than 1, then it converges, and the sum is equal to a over 1 minus r. If the absolute value of your common ratio r is greater than or equal to 1, it diverges. All right, so that's the geometric series test. And that is about the last time we're going to be able to do sums analytically. So basically, if you can get them to telescope like we saw before, you can find the sum that way using the definition. Or if it's geometric, we'll find the sum that way. Otherwise, we're just going to be approximating. Okay, the next thing we're going to do is we're actually going to look at something that you folks have been dealing with for quite a while. We are going to be looking at repeating decimals. Repeating decimals, we know, are rational. They're basically something that you started maybe looking at elementary school or at least middle school, and you didn't really think about it much. The reality is that a repeating decimal is actually an infinite geometric, a convergent infinite geometric series. Okay, so it's something that you've worked with, you're comfortable with, you haven't been too bothered by. But to actually get at what's happening here is we actually have to look at it using our calculus, using these infinite convergent geometric series. So let's first of all, let's take a look at what this actually means, and then we'll talk about how we're going to do this. So basically for all of these, I want you to write these as a geometric series, and then I want you to use the formula to determine the fraction that this thing's equal to. The great thing about these is you're going to know if you're right or wrong, because you can just plug it into your calculator and see if you're right. So let's take a look at this. So realize, we all know this just means 0.2, 0.2, 0.2, 0.2, et cetera, et cetera, et cetera. So what does that mean? Well, this is 2/10, right, plus 2/100ths, plus 2/1000ths, okay, et cetera, et cetera, et cetera. Okay, so now what that means is this is really a common ratio of 10. Now what I need is, if you remember from before, we always need that first exponent to be 0. So what you're going to do with this is, the first thing we're going to do is we're going to factor out the 2/10. Whatever that first value is, we're going to factor that out. So that'll be 2/10. Now what that will leave me with inside is that's going to be 1. The 2 got factored out, and this is going to be 1/10. That's our common ratio. This we factored out as 0, right? So that's 1 over 100. But we want to see this as a geometric series, so 1 over 100, that would be squared. Now we can do the next digit here, even though I didn't write it, because it's just, we can see the pattern. This has 3 zeros, the next one has 4 zeros. So this will be plus 1/10 to the 3rd power, and then that's going to go on forever. Okay, so now this is something that I can write as a geometric series. So realize this is my common ratio. This is my A. My common ratio is R. So this is equal to n equals 0. By the way, you can write this as n equals 1. It doesn't matter as long as you change it to n minus 1. Our A is the 2/10, and our R is 1/10 to the nth. Okay, so what we see is we have a common ratio. And if you want to, try this, just go ahead and you can, write this out. You'll see that we're going to get this up here. Okay, actually it's quite easy to check this. Plug 0 in, we get 2/10. Plug 1 in, we get 2 100ths, et cetera, et cetera, et cetera. Okay, so now absolute value of R is less than 1, right? That's 1/10. So this is really easy to do. So our sum is equal to A, which is 2/10, and then 1 minus, and then 1/10. So this is going to equal, multiply everything by 10. That'll give us 2 over 10 minus 1, that's 9, and there you go. And like I said, really easy to check here. Grab the old calculator, take 2 divided by 9, and we get 0.2 repeating. So I want to see your geometric series, and I want to see your sum. Okay, so let's look at a decimal that repeats with 2 digits and how that's gonna work out. So a decimal that repeats with 2 digits is a little bit different. Actually, what's going to change is the common ratio. So that'll be 3, 7, 3, 7, 3, 7, and I think that will be enough to see the pattern. So if I wrote this, okay, so if I wrote this, this would be 37, that's 100ths, okay? So that'd be 37 over 100, plus this would be 37 over, not 1,000, right? It'll be 37 over 10,000s, because there's another digit here. Plus, this marker's getting really bad. Okay, and then finally, this one, put another 2 zeros here. This is actually 37 over 1,000,000. So 37 1,000,000ths. And that goes on and on and on. So once we realize that, and what you can see here is, and let me factor this out, it'll probably be a little bit clearer. Let's see if this green marker is any better. So if I factor out that first term, so 37 over 100, that'll leave us with 1 plus the 37 once again comes out. This comes down to digits, so this would be 2 digits this time, so this is 1 100th. As soon as I do this, this is always going to be my common ratio, unless I made a mistake here. So this would be 1 100th, right? Because remember, we're taking out 2 digits, and that would be squared, giving us the 4 digits. And then, even though I didn't write it, I know this will be 1 100th to the 3rd. And all of these things are sort of easy to confirm, okay? So the moral of the story is, if I have 1 digit repeating, my common ratio is 1/10. If I have 2 digits repeating, my common ratio is 1 100th, okay? But once I do that work, it's basically the same as what I have over here. So sigma infinity, n equals 0. My a is 37 over 100, and that's 1/100th to the nth. And so, once again, we know that's going to converge because our common ratio is less than 1. So S is equal to A, 37 over 100, minus R. Now, let's go over here. So multiply everything by 100, we get 37. That'll be 100 minus 1, 99. And now we can check this in our calculator. 37 divided by 99, and there you go, 0.37 repeating. So that is how we express repeating decimals as a convergent geometric series. And like I said, that is something that we've been working with for a long time, but now we actually understand the idea behind it. Okay. If you want to do a little experiment here, one that's kind of fun to work with is if you do 0.9 repeating. You'll see actually something kind of surprising, or not surprising, happens if you do 0.9 repeating. Okay, let's move on. Okay, last example here, but we're going to do two parts. These ones really lead to something we're going to be doing a lot in the second half of this chapter. Example 5, find the value of x for which the series converges. So you can see here that unlike the other problems, we have a variable x in here. Please don't get confused between n and x. N is the index, that's what we plug those values in. Those are not variables, that's sort of a ticker, a counter. X can be anything, essentially, just like we're used to x. For these values of x, write the sum of the series as a function of x. So realize that whether this thing converges or diverges is going to depend on x. So we're going to find, first of all, what x values will make this converge. And then if it does converge, we're going to use that formula to write the sum. So once again, keep in mind our formula, n equals 0, a to the r n. If the absolute value of r is less than 1, then our sum is going to converge to a over 1 minus r. So this is what I'm going to use here. So even though this looks a little confusing, it really is just a matter of looking at our series here. So once again, the thing that's raised to the n is our common ratio, so this is r. The thing that's outside, that's our a. And then another thing you need to check is that first exponent 0? If it is, you're all ready to go. You don't have to make any adjustments here. So if this thing is less than 1, it's going to converge, right? That's how we've been doing these problems. So what I'm going to say is, right, the absolute value of r has to be less than 1. So the absolute value of r, which is equal to the absolute value of x minus 2 over 3, has to be less than 1. Now, this actually goes back to something you were doing like algebra, algebra 2, things like that. If I have the absolute value is less than a value, right? So if I say absolute value of a is less than 1, you know, for instance, or any value, let's call it r, what that means is absolute value is the distance the number is from 0, right? If I say the absolute value of 5, that's 5, it's 5 spaces from 0. If I say the absolute value of negative 5, it's 5 because it's 5 spaces from 0. So if I say that absolute value of a is less than r, that's negative r, it means that a has to be somewhere in between negative r and r. So as soon as I see this absolute value term, don't be thrown off by it. We want to write something without the absolute value. So as soon as I see this, realize that means that this thing has to be between negative 1 and 1. Okay. Now the way I'm going to deal with this is, you know, pretty simple. So I'm going to multiply all sides by 3. So give me negative 3 is less than x minus 2 is less than 3. We have to work on all sides. I want to remind you with inequalities, if we do happen to multiply or divide by a negative, we've got to flip the signs. That's not going to happen here, though. And then finally, we're going to add 2 to each side. So what I end up getting is negative 1 is less than x, which is less than 5. And this is what we refer to as the interval of convergence. In other words, these are the values of x that will make this converge. So this is the first part of this. So when it says find the values of x for which the series converges, these are the values of x. Okay, now the last thing I have to do is just plug it in to get the formula, right? So, or plug it in the formula. Here's my a, here's my r. So as long as x is between -1 and 5 exclusively, then we know s, let's call it s of x, function of x, is going to be 5 over, and then 1 minus x minus 2 over 3. Now, you can leave it like this, but we can also simplify it to be, and I'm running out of room, so I'll just jump right to the simplification. You can multiply everything by 3 and then distribute and do all that stuff. If you wanted to simplify this, this would be 15 over 5 minus x, and that would be our function, okay? So that's pretty basic. It's just a matter of determining what x value will make it converge using that geometric series test and then plugging into the formula. Okay, let's look at part B. In part B, same type of thing, actually quite simple. The one trick we have to look out for, if you notice, is our first exponent is 1. So we have to rewrite this thing so we can apply our formula. So what I'm going to do essentially is I'm going to factor out an x, leaving it with x to the n minus 1. Okay, so now I'm in business. So now I have it in a form that I can work with. So I don't know why I bothered doing that, it doesn't matter. So now this is my a, and then this is my r. And so the absolute value of x has got to be less than 1. So that means -1 is less than x, which is less than 1. This is my interval of convergence. Those are the values of x that will make this converge. And now s of x is going to be a, which is x over 1 minus x. And there you go. That is my function for which this thing will converge. Okay, so that is it for 8.2. Geometric series, and I guess we also did the nth term test. And that's basically it for 8.2.